The EWMA and the QSUM charts take into account the history. And because of that, the scores are correlated over time. When we raised an alarm at about observation 180 out of 200, the alarm was also raised for the next 20 observations. And so we can't just say 20 out of 200 observations are an alarm, because once an alarm is raised, the remainder is likely to also be an alarm. So instead, what we're doing is we're focusing on how long it takes until the first alarm is raised, until the first out of control observation. That leads us to average run lengths. So what we want is a low average run length if there's a signal, meaning if there's special cause, if there's a mean shift or something else. We want to detect it as soon as possible. And we want a high average run length if there's no signal, meaning if the process is in control, we don't want any false alarms. For an X-bar chart, we can actually compute this. So the Shewhart chart, right? Well, the average when you have an average. So it's 1 divided by the probability that the sample points are outside of the control limits. So when I have 1.96 standard deviation, that probability is 5%. And for the typical 3 standard deviation control limit, we get 2.7 false alarms out of 1,000. Right. I can talk about false alarms here or false alarm rate, because this is just one observation or one set of observations. So that means for the 3 sigma limit, I have an average run length of 1 divided by 0.0027, and that is 307 T, roughly. If there's no special cause, if the process is in control, we expect 1 false alarm on average after 370 runs. The average run length allows us to compare these 3 different charts in terms of their performance. The first line here, where there's a mean shift of 0 standard deviation, simply makes these 3 methods comparable here. So no mean shift means we are in control. And so these 3 numbers are on purpose approximately the same. For the 3 sigma control limit, we get run lengths of 370. And for the QSUM with these specifications, we get roughly the same run length. And for the EWMA with alpha equals 0.2, we get also roughly the same run length. And now we have various mean shifts. So special causes here, and then the run length changes. And what we're hoping, of course, is that we can detect it as fast as possible. Clearly, the larger the signal, the bigger the mean shift, the sooner we can detect it. And here we see that the X-bar chart doesn't work very well. For half a 0.5 standard deviation in mean shift, we take 155 observations on average to detect it, whereas for the QSUM we have 35 and 36. So very similar performance, QSUM and EWMA respectively. And that carries forward for larger standard deviations. This is much larger than over here. Well, actually, I said it's much larger. It's much larger for 1 standard deviation, it's larger for 2 standard deviation, and then it evens out, slash is slightly even better for 3 standard deviations. Now, 3 standard deviations is not common, right? So when you detect a mean shift, it would usually be a subtle mean shift. So for very large signals, the X-bar chart works well, but for more likely signals, we want to go to QSUM or EWMA. And when I say signal, I mean a mean shift. All right. So here's a question for you. assuming a Gaussian distribution, what is the average run length for a 1.96 sigma control limit? And I'll leave you to answer that question.